So very warm welcome everyone to this session of the PROTEUS seminar series. Our speaker today is Callender from the University of California, San Diego. Very welcome, Craig. I will leave it to him now. Thank you very much.
Thanks for having me. Oh, these dogs are really going to be a pain. Let me share my screen. I'm very happy to be here. And well, I wish I was there. It would be more fun, I think. But okay. Well, first to begin with, we're going to try to do a kind of chalkboard talk, but I'm going to try to aim sort of like in the middle. So I think I'll just try to hit like the basic ideas, and then we can discuss. And so if there's more, so if you want more technical detail, then I can talk about that in the Q&A, or also there's a paper. So the talk is called No Time for Time from No Time. And it's with a PhD student, Eugene Chua. And we're also giving it at the PSA in Baltimore next month. And anyway, so yeah, so you have so that you can read the paper if you want more detail than what I give now. Also, what I thought it would do and maybe be useful would be to make some general comments that are not in the paper, because the paper had to be shortened, which was probably a good thing. But I have a few other things to say that are more general, maybe. So first, this is a congratulations cake for Sylvia getting married. So congratulations. But I also use this cake for the talk. So in the philosophy of physics, philosophers have been struggling to make sense of this idea that there could be time from no time in quantum gravity. And so if you think of the, if you think of the sort of bottom level as of a cake, think of a layered cake, and it's got no time. So fundamentally, in the set of fundamental solutions of the quantum gravity theory, maybe there are no solutions with any time. But of course, we need a time. Otherwise the theory is going to be empirically incoherent, because all of the data we have is all data in time. Some of the data is actually, things like change, which then also involves time. And so somehow, at the top of the cake, you need to get this kind of emergent time. And so somehow you need to go from no time to emergent time. Now, I don't really know that literature and philosophy of physics about this too well. I mean, from what I've looked at, though, you can see that philosophers are struggling, because what they're often doing is looking at the, literature and emergence in philosophy, from the mind-body problem. And so then they're looking at things like, functionalism, composition, supervenience, all these sorts of categories as ways of somehow getting the emergent time to emerge from no time. But all of these things, they're all synchronic relations, which is good from the point of view of not being circular, but they're not really the sort of emergence that you usually see in physics. And so when I think of emergence, I think more like a physicist, and I'm thinking more like, the emergence of temperature, microscopic properties from microscopic properties. And all the cases I know of, those types of emergence are always diachronic, right? So the temperature emerges over time from the lower level. And so most of the cases of emergence I think of in physics, and when people talk about time emerging from no time like say temperature emerges, or like color emerges, or things like that, then those things are diachronic. And then that raises the worry that there's some kind of sneaking of time into the derivation of emergent time from no time. You worry that the derivation might be circular if it involves, if the way you get it through this arrow here involves time already. And so I've always had this kind of suspicion about that. And so that's what I want to talk about, is this idea that many of these programs in quantum gravity that say that they're fundamentally timeless and then try to get an emergent timeout, that in some sense they cheat, that they, not on purpose, but they employ some kind of assumptions which you're not really entitled to employ. In particular, if you think, you've got some equation, say it's the Wheeler-DeWitt equation with no time in it, and then you're going to get some equation, something like the Schrodinger equation, to emerge. They're not begging the question in any sense of like pulling out a T, where they're not assuming a T and then putting in the T. But what I am thinking about is something more subtle, which is that the justification for the assumptions that are used in the derivation are only justified when you've already got a background time in place. So it's not a kind of straightforward begging of the question where you're assuming, where you're assuming it in the premises and in the conclusion. It's more subtle than that. It's more like, what is the justification for some of the premises? And you need to justify those premises, of course, because I could go from any equation to any other equation if I'm allowed to assume anything, right? So if I can assume anything, I could get anywhere. Okay. So, oops. So what I'll be thinking about is my case study is semiclassical time, and this is in the old canonical approach, canonical quantum gravity. And so, as you know from being part of this group, there are various approaches to quantum gravity. One of the original older ones is canonical quantum gravity, and sorry, let me just. And in that approach, you of course find this problem when the Wheeler-DeWitt equation seems to have no time in it. So here the Wheeler-DeWitt equation is you have this it's an attempt to, it's a constraint from the canonical quantum gravity formalism, and what it is you're projecting this constraint onto you're keeping the wave function of the universe within the constraint, and so that you're satisfying this constraint. And lo and behold, you end up losing the time. In this approach, we can think of the wave function is going to be a function of a bunch of spatial 3 metrics, and then we'll just have a phi be a scalar matter field. And so you can think of that as sort of the quantum field part. Now, you get this equation and then there's no time. So now there are many different approaches to try to get a time out. And one is this kind of semi-classical time program. It was, the sort of idea came from DeWitt, but that wasn't the covariant approach. And where I learned of it was, where I think it was most nicely done was by the physicist Thomas Banks in the 80s. But then you see many other groups have done this as well. Uh, and the idea is really quite beautiful, I think. The idea is to make some assumptions and say that the idea is something like at the classical level, time emerges. And the idea is really quite beautiful. So if you think about, the connection between energy and time, this looks like the time independent Schrodinger equation. And if you think, well, there's no energy, if H is 0, then, then there's no time development. But that doesn't mean that if we split the world into subsystems, that we can't have non-trivial energy and therefore non-trivial time development in the parts. And so the idea is really, I think it's a gorgeous idea. And the idea is that, fundamentally, the system of the world has no time. On the other hand, when you carve it up into subsystems, then time appears. And so when you carve it up into subsystems, some subsystems can be seen as clocks for other subsystems. And that's the basic idea. Idea is that, because the Planck scale is so low and we're so high, the idea is that, we're not going to see, we can use the background gravitational part as a kind of clock for the quantum matter part. And so again, fundamentally, there's no time, but if we kind of blur our vision and carve up the world into subsystems, then time appears. In particular, we can get a time to appear for the quantum matter parts, where we think of the gravitational parts as the clock. And you can make that precise. And what's nice about it is you can make that precise by thinking that what you want for a time, what is time? Well, the idea is a kind of minimum sufficient condition for time, which I think is very plausible, which is that if the matter fields act with respect to the if the pattern of dependencies is such that it mimics the Schrodinger equation, in particular in the way the Schrodinger equation has a dependencies with respect to time, then it is time. And so it's a kind of functionalism about time. Where if you look like the T, basically if you look and act like the T in the Schrodinger equation, then that's good enough, your time. And I think that's quite plausible. Now, okay, let's go into how this program works. Let's see. So we are we're in a we've decomposed general relativity into its 3+1 Hamiltonian form, and so we have a we're imagining a set of so the fundamental variables are going to be the spatial 3 metric, and then it's the extrinsic curvature is its kind of momentum. But now we've got this Hamiltonian constraint, and so we've got this kind of the Wheeler-DeWitt equation. This is the wave function of the universe. And then this equals 0. We've got no time. Now, how does the semi-classical time program get timeout? Well, it makes a couple of assumptions, and in particular, it makes about 20 assumptions. Anderson has a paper where he counts the number of assumptions, and I think he gets over 20. But the crucial thing is really, there's really like a kind of 1-2 step. And it's easier to understand the idea if you do it this way, in terms of this 1-2 step. So we're going to take this wave function, So you got this wave function. And we're going to make some approximations based on the thought that, you know, the Planck level is so low, so far away from the sort of level of our experience. And the first one is this Born approximation and Born Oppenheimer approximation. And what the key thing here is so separate the wave function into two parts, chi, a function of HAB, and psi, then retaining the quantum part. And so the main assumption here is a kind of factorization. So assume that the wave function of the world factorizes into two, and in particular, it factorizes into a part that's just a function of the spatial 3-metric, and then the rest. And then, so this is the Born Oppenheimer approximation. And then we do a Wkb approximation, which is another kind of standard approximation you use in pull out any quantum mechanics textbook and you'll see this. And what we do then is we take this part and do it and Wkb it. And so then we say it's this is the Planck mass, and then S, the action, HAB. And then now that will bring down all this. And so the end result is we're going to say that the wave function is approximately having this form from doing this kind of double approximation. We're assuming that A is slowly varying with respect to S, that S is real, A is positive and real, and also that this Wkb term is an eigenstate. Okay, so there are a bunch of other approximations there. And so now what we do then and then the way the theory then works is we, expand as usual in the Wkb approximation in terms of the order of m squared p. And we plug in the SO and the S1 terms back into the Wheeler-DeWitt equation. And when we do so, what we get is a Hamilton-Jacobi type equation. But now this time it's going to be the Einstein Hamilton-Jacobi equation. And then you get a kind of continuity equation as well, which is good for getting probabilities. Then, so the idea now is to take this these equations you have, and what we'll do is we will look in a solution in this, and so everything will evaluate in a solution, and then we'll define. You'll see then that this the Einstein Hamilton-Jacobi equation will define a kind of vector space, and then it's natural to then from the rest of physics is then we know then it's natural to then define a time as the sort of direction normal to the surfaces of this Hamilton-Jacobi the surfaces of level S, the direction normal to that is often thought of as a time. And we'll see all those surfaces. And so we'll get a kind of time there. in that solution. And so this is sort of just, a gravitational time. And then the other thing that is then done is you then define you define from a WKB, sorry, so that's you get this kind of what's then called a WKB time. And you are then able to use that time and then show that the matter fields are going to obey something like a Schrodinger equation for that. So there's two steps there. One is I define this kind of time through the superspace, through the solution, through a particular solution in superspace, and then I'll show that the wave function with the phi term, the matter fields, that the quantum wave function will, when I compare it to that time I've just defined, will actually end up obeying something that looks like the Schrodinger equation. Now, the actual math to do all of that is, with the first step I can follow. The second step is so much math that it's frankly beyond me. But I could reproduce it, so you can see the derivations in a whole bunch of different places. And so I've got references in the paper. It won't be that enlightening if I just kind of slop through all of that. But the end result is you end up getting this. You've defined this T here. This T is the T that is naturally suggested by the direction normal to what you would think of as normally you would think of as the evolution of the Hamilton-Jacobi equation. That is where that T is. And what you're able to show is that the wave function evaluated at a particular solution of superspace, so that's why I've got the semicolon and then the HAB, is then equal to, and deriving this part is like a real mess. And you can see it's a kind of Schrodinger equation. And so then I gave you that sort of minimal sufficient condition for time, which is that there was if you look and act like the T in the Schrodinger equation, then you are time. Well, this T, it looks and acts like the Schrodinger, it's in a Schrodinger equation, and so it's time. And so it's beautiful. You get this, derivation of time popping out from just these two core assumptions and then a bunch of other more technical ones. So, another way to think about it, just in terms of pictures, in case all the technical stuff is not really your bag. Imagine in the canonical approach, the configuration space is superspace. It's a set of all spatial 3 metrics. And so you can imagine, each point is some kind of geometry. Maybe. Maybe it's some kind of weird thing. Now you're saying in one of these, I can find a kind of, if I make an approximation, I can find a kind of thing that seems like it's the kind of foliation. I can find a natural way of carving this up. And then there in that solution, I can then show you that the quantum fields will respond to that very T in a Schrodinger-like way. So it's very clever. It's really beautiful. However, what justifies these assumptions that we just made? So we need to justify well, I think I'll just go through this. Maybe so the fundamental thing can get so my fundamental point can get out. Just go through this kind of intuitively. So the Born-Oppenheimer one is that you can factorize into a product. So you're saying the wave function of the universe can be factorized into these two parts. Well, what justifies this? Well, I think this one's the easy one to see that where time sneaks in, or maybe I shouldn't say time doesn't sneak in, but the question is more like, is it justified in the absence of time? So why would I take this wave function and put it in product form? Why is that a good approximation? Well, at first, it doesn't seem like it involves time at all. So when you look at the literature on this, they just say, well, the masses, there's a difference, there's a separation of scale on the masses. So you have a separation scale of the masses. The gravitational masses are very big. Quantum world is very small. So there's a kind of separation there. And that separation is really what justifies being able to break this up into this product form. So it doesn't seem like time sneaks in. On the other hand, why does separation in the masses cause this? Why does this justify a product form? Lots of things are different. So if we think of charge and all sorts of other things, why does mass end up having this effect so that this is okay? And what makes you suspicious, of course, is that if you go back to your elementary, your quantum mechanics course, where you probably first saw the Born-Oppenheimer approximation was in dealing with the nucleus and the electrons. And so it's used there, and the idea is that the nucleus is big, and then the electrons are small in mass, big mass. Oops. And so you end up assuming that the you use it there, but what's really going on there is a separation of timescales, because the core idea is that small things move fast, big things move slowly, right? So when you look at all the different types of ways of doing the Born-Oppenheimer approximation, you're sort of assuming the nucleus is sort of still, it's stopped, and then because it moves so slowly because of its mass that you can just treat it as effectively stopped, and then have the electrons whirling around it, and then now you can sort of slowly vary it. So you unfreeze it, and now solve again for the nucleus somewhere else, do it again and again and again. But what's really going on there is that it's not so much that it's that the mass is a proxy for the separation in time scales. So it's basically, so what I'm saying is, the justification is that the heavy system moves slowly and the light system moves quickly. And then, so then you can then, calculate a realistic nuclear wave function by letting it vary slowly or sluggishly or that. But the core thing there is then that really you can see that time is assumed there. And so now we can't then prove that there's no way to justify it in the absence of time, but the only way we know to justify it is with time. And so that raises the suspicion that time is sneaking in. And it also leaves open a kind of challenge, can you justify this product form in the absence of invoking time? Okay. So that's the first problem, and that's probably the easiest one to see. We have a lot to say about that, but the basic core idea is very simple. The one that took more time for us is the Wkb approximation. So there, remember, we've got the HAB being given a Wkb approximation. And so oops. Now we're assuming A is slowly varying with respect to S. S is real, A is positive and real, and that this is a kind of eigenstate of this. It's not a superposition. What kind of puzzled me at first about this was that, when you see it in textbooks, usually the Wkb approximation, it looks like, well, it actually was originally discovered by mathematicians way before quantum mechanics. And so it just looks like a kind of, a kind of piece of partial differential equation theory. So it just looks like it's a piece of math. Here's how we can approximate solutions to this one equation with this other equation. And so it's often advertised then as almost like a part of partial differential equations. And so it's kind of hard to, it was probably easy for other people who are smarter and know this better. But for us, for me, it was a bit of a challenge at first to sort of peer behind that and exactly see where the physics was. Because even if you do have, this equation gives approximate solutions to this other equation, but you still need to have that justified physically. Ultimately, it's going to be a physical justification. And so we wanted to see, where is the physics here? And at first, what catches your eye is you see that the assumption is that, A is slowly varying with respect, is slowly varying. But then that's not actually inducing any kind of time dependence there, because when they say slowly varying, that's with respect to X, the spatial coordinate. And so it's about the shape of the potential at a moment, not through time. And so it's slowly varying spatially, not temporally. But once you kind of peer through all of this, you can then see that, what's really going on is, well, there are different ways to see it, but and you can go into my paper and see the details. But the idea is that, why would you think that A varies slowly with respect to X? Well, that only holds when the potential is approximately constant with respect to X. And when the potential is constant, then the system behaves like a free particle. A is constant. When the potential is approximately constant, the system behaves approximately like a free particle. So A varies slowly. And so what's really going on is you're saying, how long does this Wkb approximation hold? And the idea is it holds for a certain amount of time, the amount of time that we can pretend that the potential is constant. And so in the background, there's still this time, but it's a little bit harder to see. There's two places where it really pops out clearly. One is that when you actually do the derivation, and I won't, you whip out the classical momentum. And then of course you've got a T from the classical momentum. another way to see it is that, well, the way what I found helpful was just actually going back and looking at the Griffiths textbook. And in the back, he's got a section on the Wkb approximation. And he complains about the unintuitiveness of the normal way it's done that sort of hides the physics. And then he says, here, I'll read a quote. He says, the probability of finding the particle at point X is inversely proportional to its classical momentum and hence its velocity at that point. This is exactly what you would expect, that the particle doesn't spend long in the places where it is moving rapidly. So the probability of getting caught there is small. He says, in fact, the Wkb approximation is sometimes derived by starting with this semiclassical observation, instead of dropping the amplitude A term in the differential equation. The latter approach is cleaner mathematically, but the former offers a more plausible physical rationale. So I thought from studying this, it was kind of interesting to see, actually a kind of point, a philosophy of science point that's not related to quantum gravity, which is just that the way approximations are often sometimes justified in the textbooks are not, sometimes they obscure the physics behind the justification. So they sort of takes on a life of its own, and then develops. Okay, now I can go into that in a lot more detail if you want, but I realize that was probably not, except for people who have studied WKB, it probably was not too illuminating. But the core idea is that there is a time there, and it's found in the fact in how long is the approximation good. Oops. Oh. Okay. Then finally, I'll mention the third approximation, but I'll just talk it through and not even do much with it. Well, now notice that the semiclassical approximation cheated in a couple of ways, because we assumed we were in eigenstates of the Hamiltonian operator. But why do that? So there's not any particular reason to, so we assumed you're in we assume this, not Wkb. And we also do the same for the WKB. So you could have been a superposition of the instead of A, etc. It could have been etc. So we assumed eigenstates at two points. But what justification is there for this? Well, people sometimes say decoherence. You decohere into one of these. And here again, it should be clear that decoherence is a process in time. And so if you really want this, then you're assuming time again. I mean, I don't know how serious to take this one, because I think they could always just say, well, it's a kind of lucky accident that the universe started this way or something, and then not do this. But decoherence is definitely a dynamical process. And there's, so now you're sneaking time in if you want to answer this problem. It is actually kind of amusing that, so my student Eugene found, so Klaus Kiefer is, done a lot of beautiful work on the canonical quantum gravity and the semiclassical time approximation. Eugene found Klaus Kiefer with this kind of circularity in the same paper. So we have a quote in the paper where he says, a prerequisite, of decoherence in the semiclassical time program is the validity of the semiclassical approximation. So a prerequisite of decoherence is that you need the time from the approximate time parameter from semiclassical. And then, so this was on page 311 of his 2005 paper. And then 7 pages later, he says, since decoherence is a prerequisite for the derivation of the Schrodinger equation, we might even say that time, the Wkb time, arises from symmetry breaking, which is what he means by decoherence. So he says time arises from decoherence, and then so he's got the reverse order 7 pages later. So there you can see he has to grapple with this kind of circularity itself. Okay, so we think to sum up, we think that to get time out, you need to get time in. You can't really get it out without. You can't justify the premises and the approximation without assuming time. In the paper, we also mention and compare it to a few other things. And so, for instance, one thing that's kind of interesting, I think, is, think about, let's forget about quantum gravity. Let's think about the Everett interpretation of quantum mechanics. So Zurich and Baker and I'll have to look at the paper. One other person, have charged the Everettians who try to get probability out with circularity because they assume decoherence to get probability out. But what is decoherence? It's the idea that the probability of the branches interfering is small. So then you're assuming probability to get probability. Now, if you especially think that how closely connected probability is to time, it's very similar to the sort of charge here. So there you have, so in this case, you need time to get time. There you need probability to get probability. Now, Wallace then replies to them and says, yeah, but we can still talk about distance between branches in a way, that doesn't presuppose all that Everett work that they do. And he relies on the Hilbert space norm to give you the distance between branches in a way that's independent of the probability. Could you imagine somebody doing something similar here? Well, the reason I mention it is because the answer is a resounding no, because of course the Hilbert space problem in canonical quantum gravity is tied to the problem of time in canonical quantum gravity. So we don't have a positive inner product that we would want in the canonical quantum gravity. In fact, the best way to solve it would be to find a time and then use that time to then define the inner product. So here you don't have any resources to use. Like, I don't know whether Wallace's answer is a good answer to that Everett problem, but at least he's got something he can point to that is independent, which is that Hilbert space norm. Here, we don't know we don't have anything like that. The two things are tied together really tightly. So, and then two final observations. One is, I had the two in my head. I had the one, and then now I just lost the first one, and now the second one has appeared and taken over in my head what the other one was. Wait, what was? Well, okay. Yeah, so oh yeah, I know, now I remember. Yeah, two final observations. One is that in some sense, the analysis here and what's going on in these emergence programs are all a bit half-baked. So even what I'm doing here, just think about when you make an approximation, you make an approximation with respect, there's a kind of elephant. What I want to say, the first point is there's a kind of elephant in the room that's not being discussed, which is that, which is basically the measurement problem. So normally, which does get, it's all being bracketed here, but it's not really entirely fair to bracket it. Because think about when you normally make an approximation, suppose so in the paper we give an example of, assuming that a classical pendulum is can be modeled as an undamped harmonic oscillator. Well, you can sort of do that because if the angle is small, then psi theta is approximately theta. And so you can do that. And what does that mean? Well, what does small mean there? Well, small means relative to some kind of standard. And that standard is, if that standard is a kind of perceptual or observational standard or something like that defined by an observer, then you need an observer there to provide that standard. And so we haven't really done that. And of course, that also raises the worry we have in the paper that, in getting an observer, it doesn't make sense to have an observer who's just instantaneous. So an observer is something through time. And so that's a kind of elephant in the room that hasn't been discussed. And then the second point I want to make is that, I began with that kind of sheet cake model of emergence, where we have all these layers of the cake with no time, and then we get some kind of emergent time. But I think a better way to think about things, and this is really a kind of advertisement for old work I did on Bohmian quantum gravity a zillion years ago when I was a grad student, is forget this kind of layered cake model of emergence. Think instead of I don't know what it's called in Italian or Spanish, but in English it would be called a sheet cake, where there are no layers, but there's still a perfectly good sense in which you could talk about emergence in terms of a sheet cake. So that is, imagine there are solutions where there are where time works, and there are some solutions where there's no time. So for instance, think of, when you talk about the electromagnetic arrow of time. So there, with Maxwell's equations, we have some solutions where we have retarded solutions, we've got advanced solutions, and then we've got mixed solutions. So we have a bunch of solutions where there is no arrow of time, but then we have a bunch of solutions where there are. And so in all of those cases, it's sort of fundamental. It's all at the fundamental level of the solution space, whether there's an arrow of time or not. But we say that the arrow of time emerges in this, but not emergent in this kind of layer cake sense, but as a process through time, with some kind of diachronic thing, which is then cheating, but rather just that some solutions have time, some of them don't. And so you could have the same kind of thing happen in quantum gravity. And in particular, in quantum gravity, a long time ago in the early 90s, a bunch of Bohmians all saw the problem of time, and about 6 groups all had the same idea at the same time, which was and even non-Bohmians had this idea of just to let the phase of the wave function define the time through the whole solution space. Now, depending on what the wave function is, you might have no time. So if the wave function is real, you would have no time. But in cases where the wave function is complex, then the Bohmian theory would give you a time. And those things would be defined through the whole solution space, not just in the kind of classical sector. Like, so like a non-Bohmian, like Greensight had this idea, but also a bunch of the rest of us did. And so I think this problem, to conclude, I think this problem is bigger than just what happens here in canonical quantum gravity. I mean, Alvaro and I were talking last week about, Rovelli's thermal time hypothesis. Well, if you follow some of go through the math of that, which I looked back at after we talked, and then you see, it's going to define times all over the place, even times that are not ones that correspond to what we think of as time. So you need to do it between what equilibrium states, not as opposed to non-equilibrium states. But then what makes an equilibrium state? Well, time. You see this again and again in some other approaches. People talk about time emerging at a certain energy level. Where's the energy? How do you define the energy without the time? Well, maybe you could do it, but maybe you can't. And so I think this kind of cheating problem is, I don't know if it's omnipresent, but it's much more common than just this. Thank you.
Oh, thank you very much. It was a very rich presentation, actually. I'm sure you stimulated a lot of discussion, so we can start. So who wants to ask questions, comments? Do you have some comments to the presentation? Nobody.
I have some.
Yes, please.
Question or clarification. Regarding this picture of born Oppenheimer, it's in my understanding, if this kind of approximation, it's like a matter of how one see the systems, in the sense that if you are stating that we have free electrons and heavy nuclei, it's a way of how we are seeing the system. So in that sense, for me, it gets like some complication on how to think these kind of approximations as processes, in the sense that when one deals with the Big Bang, we are understanding here a process where something goes from any state to general relativity. So I was wondering, how do you see this kind of approximations in the sense if it's only a way of how we look the systems, or there's some kind of process involving in here? And if the answer is yes, if we have like different solutions, one supposing the presence of time and others which are not, if there's any connection between this kind of states between the states with times and the states with no time. So there's any link between these kind of things, or there's just a way of how we look the system?
Yeah, I think what's really crucial. So you've got where we present you. So you've got this super space and a wave function on it, and there's no time, or apparently that it's said that there's no time. Now you've got all those correlations that are in the wave function, and the Born-Oppenheimer thing is basically saying, well, forget about a bunch of those. So for the physicists, so you're doing a product, so you're saying like, forget about the off-diagonal terms. Now, what is this forgetting? Who's forgetting? And so it's got to be with respect to something. What is providing? Why do you think that those terms or those correlations, some of them are small or insignificant or ignorable, and others are not. That's really like the fundamental thing is what makes those things ignorable. They're just as good, from the point of view of nature. Those correlations are just as good as as all the others. So why are you saying, well, let's just forget it? Don't look at those. So they say, Luciano, don't look at those correlations. If so I put my hand over those correlations, and now time pops out. But what justified putting the hand over those correlations so you couldn't see them? And I'm saying, you've already assumed time in saying that you can put your hand over those correlations. I don't know if I answered your question.
Well, yes and no. On the one hand, yeah, I can understand this way of thinking, but on the other hand, most cosmological models, for instance, do practically the same. They are just take a mini superspace, and they're just do math in a mini superspace without arguing why the suppression of space. But maybe there's not an elaboration on this kind of answers, and that's why the controversy in how we understand emergence.
So you're saying, so already, maybe you're saying already you're making assumptions even prior to this, and saying doing like a mini superspace model.
What I'm saying is that once that times only appears after the approximations. So if you make like this kind of hiding things, you get time, but there's no. I was thinking how to understand this way, or physically, how to link a model of the Big Bang with this way of hiding things, how to give a consistent interpretation, like a physical interpretation to this way of suppressing things, which makes times to appear.
Well, I mean, I think that the intuition is that the gravitational degrees of freedom are, this kind of heavier, bigger, the quantum stuff is all going to be down, at the Planck scale or something. And so that those terms that involve both the phi and the h are all going to be so far down that they're not going to be, you're not going to notice them so much.
Yeah.
And so I push them aside. And when I push them aside, then I'll see this sort of Big Bang and what seems like temporal development.
Thank you.
Yeah, and maybe another kind of, maybe a kind of useless metaphor, but the idea is sort of, what I'm trying to say is, the idea is sort of like, if I blur my vision, their idea is that if I blur my vision, then time will pop out. So I don't look down at that little tiny level with where phi and h are interactions are really significant. And what I'm saying is, no, you're actually, putting time glasses on. It's not that you're just sort of getting that, so I learned that, what was the, what's the movie with Dorothy and the Wizard of Oz? Is it called The Wizard of Oz? Yeah. So when you go into apparently in the book, when you go into the Emerald City, everything looks green because they take people, they don't do this in the movie, but when they take people and they put glasses on them with green filter, so they only see green. And so this is sort of what's happening is you're being put, some time glasses are being put on you. It's not that it's sort of emerging from blurring. It's they're cheating, they're putting the time in.
Okay, Federico.
Yeah. Hi, Craig. It's very nice to meet you.
Hi.
I'm mainly a metaphysician, so I'm not very expert in philosophy of physics. So I'll try to make a very general question to not slip in any of the details. I just wanted to ask you if you think that is there any one of the approximations that you discuss that needs for its justification the assumption that of a temporal metric? So I had kind of the impression going through your talk that what you really need sometimes, for example, in the case of probability, you may have I don't know, you could say in T0, the probability of an event E to happening in T1 is P, where you have the notion of T1 being after T0, but I mean, it's not obvious to me that you really need the distance to define the distance between these two moments. Or in the case of the dynamic of the system, when you discuss the approximation of I don't know, OP was the principle of the BO, sorry. So when you discuss BO, you talk about the dynamic of the system and the fact that we take into account heavier mass because in the dynamic of the system they are more relevant for the development. But even in this case, I don't really see the need of temporal metric. So if you could say something about it.
Yeah, I think you do need a temporal metric to justify the use of these approximations. So if we think of the Born-Oppenheimer one, then if we think of the kind of the nucleus and electron, then the idea is that the heavy system moves slowly, the light system moves quickly, and so making sense of that then seems to imply a kind of time metric. At the very least, it implies a kind of separation of time scales, but I would think that making sense of the quickly and slowly, and uses a time metric. Otherwise, what does fast and slow mean? Now, when we go to the quantum gravity, of course, they're not then saying fast and slow, they're just saying heavy and light. But what is the relevance of heavy and light if not connected to fast and slow?
Okay, right. Yeah, I was thinking about a possible way to make sense of the notion without temporal metric, but yeah, I mean.
Yeah, so you can see it's kind of subtle because they're not coming out and saying fast and slow. They're just saying heavy and light.
Yeah.
But then you have to say, well, why should I care about heavy and light? There has to be a reason why that matters. And then, what they're doing, I think, is basically you get used to using the Born-Oppenheimer approximation. It seems okay to use when I see these two the separation of mass scales, but then you forget why the separation of mass scales was ultimately vindicated that approximation. But the real reason, and I think there's no controversy about this, at least in like undergraduate quantum mechanics use of Born-Oppenheimer, that there is a separation of timescales there. So I can't say that they definitely cheat, but I can then say, if you don't have a separation of timescales, you at least are lacking a positive reason for me to then think that Born-Oppenheimer is justified in this case.
Okay, and in the case of probability, you have an opinion about if you need temporal metric, because
Yeah, I think that you need to have, yeah, without time, you're not going to have probability. You know, I mean, a quick way to see the connection is, you know, that you need, you know, if you were thinking about rolling a die and you had all the different outcomes, you know, all the outcomes have to be normalized. It have to sum to 1, but that's at a time. You know, so through space you don't care.
Yeah, sure, but I mean, you have to, so you define the probability of having a certain result of the throw at some time that is successive to the time of the throw, but you don't need to define the distance between these two instances. That was my point. So maybe in that
That's
case,
true, yeah. So you don't need a time metric for probability, but well, maybe. So your point, yeah, they just need a kind of ordering.
yeah,
Yeah,
that's what my question. Okay.
yeah, that might be right.
Okay. Yeah. Thank you.
So we have the 3 questions. Siddharth, am I pronouncing it correctly?
Yeah.
And then Yazan, and then Nicola.
Okay. Is it my turn? Okay, wonderful. Thank you. Yeah, so I'm curious about whether if you take a somewhat functionalist approach to this question, would they really be moved by the charge of circularity? So I think in a lot of functionalist reduction, you're doing something that's kind of a posteriori, because you kind of know what the target you're looking for looks like, and then you're trying to identify structures in your cake model at the bottom level that sort of fit that criteria of adequacy, right? That sort of behave in the ways that you want it to behave. So I imagine that someone I'm not very familiar with this derivation, so it might turn on the details, but I'm imagining if based on your presentation, someone might say, well, look, right, I'm trying to find a parameter that fits the role of time here. And I'm going to go through some mathematical moves that let me identify that. And in a way, right, because I know what the target is, in my derivation, I'm going to use arguments that, you know, seem to be appealing to time, but that's only because I kind of know what my target looks like. It's not that I'm building in the idea from the word go. The structures that I'm trying to identify are present already, but I'm using my knowledge of what I'm looking for to identify them. So for example, something like, so you said that in the Wkb approximation, it's sometimes presented as just this mathematical thing, right? So that would be friendly to this kind of approach, because they would say that for whatever reason, this approximation works here. And because this approximation works here, I can use that thing with respect to which it sort of varies as a kind of time parameter. I haven't fully articulated the thought here because I have to go back and look at the details of the derivation to fully see how this line of reasoning would go there, but I'm curious what you think about this.
Yeah, that's a great question. Yeah, it allows me to say, yeah, better what's going on here. Yeah, so you're right, of course, that so for instance, I'm using a functionalist definition of time. I'm saying if you look like and act like the T in the Schrodinger equation, then you get to be time. And you're right, so I'm going to have that kind of knowledge in any kind of functionalist picture. So if I was doing a kind of functionalism about mental states, I would have a kind of idea already of what the role would be of mental states, and then I would go down into, say, the neuron level and then look for something that played that role. But the way you put it, it allows me to say kind of precisely what the difference is between what is done here in this program versus what you've just described, which is that those structures they find are not there. So when you look, so the way you put it is there's, I already have some knowledge of time when I'm looking for those structures. And what I'm trying to say is those structures are not there on the bottom level. They're only there because I pretended they were there, and I wasn't justified in pretending they were there. As opposed to, say, in that sheet cake model, they're, like with the electromagnetic arrow of time, they're all fine, like a really retarded electromagnetic solution. It's really there. The structure's already there. I already know, you're right, I already know what I mean by the direction of time. And then I go down into the final bottom level and I find that structure. But here, my accusation is that structure is all made up, because it's been, I've smuggled in time to use a bunch of approximations to even, so not to define the functional form of time, but to, to see, I've got these made up creatures down there at the bottom, these structures that aren't really there.
Yeah, I think that's helpful. So maybe perhaps, the way to think about it would be that, in a way you're saying, they're saying that the structures have to be like this in order for you to be able to get out the time, but there's no, so in a way, the best, if I get you correctly, your argument could be paraphrased as saying that in order to get time out, there has to be far more structure in the bottom layers of the cake than you're allowed to assume beforehand or a priori, in a way. Is that a fair way of?
Well, what they're really doing is they're getting rid of structure. So, okay. So it's sort of getting rid of all of these terms and all this stuff. That's something that they sort of are able to massage things into looking like it fits the functional role of time.
Right. Okay. Well, anyway, I think, thank you. That's helpful. Others are waiting.
Yeah, thanks. That helps me clarify for myself what I'm doing.
Yazan.
Thanks, Craig, for the great talk. I was just wondering whether you were sympathetic to the research program that some metaphysicians are currently carrying out in order to get rid of time completely. So they want to design a completely timeless picture related to quantum gravity. So since you're talking about how you think that the approximations have somehow circular assumptions, and that emergence approach, especially functionalism, might be problematic. Do you think that it might work to just get rid of time completely, to start thinking about timelessness as a possible research program?
Well, I guess it depends on it would depend on what program, I guess. I don't think I don't have a problem with the idea of getting time from no time in the sense of, like that sheet cake model, because there's really time in the solutions where there's time in the solution, where there are solutions with time, there's really time. That's all the way. It's fundamental in the sense that where it exists at the fundamental level. And so if we wanted to call that no time physics, as long as we're careful with our English, we would be okay. I don't like the idea of getting. And also there's another thing to say, which is that, some philosophers historically anyway, have had too high standards for what time should be. And then they automatically get no time, right? So if you think of something like McTaggart or the kind of Gödel argument, they have very high standards for what you have to be time. I have extremely low standards for what you have to be time. I mean, I already think that the time of general relativity is barely earns the name. You know, when you think carefully about general relativity. But I'm afraid I'm not answering your question because I'm probably not targeting the right groups.
No, it's fine actually, but I just want a clear follow-up. So just to make sure I understand your position correctly. So when you talk about the sheet cake, you're saying that you think that time is fundamental. It's not emergent, and so it's fundamental. It's there in the structures, but we have to look elsewhere. We don't look. We have to look at electromagnetism or thermodynamics in order to salvage time. Am I getting this
no,
correct?
I'm saying that it could. I'm saying that following makes sense. You could have a fundamental theory where some of its solutions have a time and some of its solutions do not have a time.
So
you wouldn't then say time existed in every possible world of that theory. You know, so just some possible worlds would have time. But in those worlds that have that time, they really have it. I mean, they have it fundamentally.
But what about our world? Like,
So I think our world is one of those worlds that have the time.
Okay.
And also I have to say, you know, I'm very sympathetic to like Alvaro's position and the kind of position that really the argument that time disappears, that the time is not there it's a bit quick, the argument that the time disappears in quantum gravity, and that it's really, so some of these kind of rescue attempts are maybe not necessary because time might already be there.
All right, thanks.
Many of these approaches think that time disappears because they treat temporal development as gauge, and that might not be right.
Okay, if I can, I continue with my question.
Mm-hmm.
And I have two questions. One is more specific, and the other is quite general, and they are related in some sense. And is it possible that the problem you highlighted of the Oppenheimer approximation is just a confirmation of the fact that the time t is not a physical time, but it's just a parameter? So, well, even classically, the time t is just a parameter because the time that you can observe. So the physical time is the general relativistic time. So it depends from the metric. And so the approximation, the Oppenheimer approximation, in some sense, can be seen as having a no physical weight. So you are not reintroducing a physical time because you're dealing with the time t. The time t is not a physical time, it's just a parameter. And so this is the third question. What do you think about this? So it's not a problem that you are reintroducing time in a framework with no time, because the time you're dealing with is not a physical time. It's just a parameter. So it's not a physical approximation, just a mathematical, let's say, approximation, the Oppenheimer approximation.
Right. I think I can see what you're saying, you know, and I don't object to whipping out a parameter and calling it time and parameterizing some physical structures. Yeah. And so that happens, and I'm completely happy with it in the derivation when, you know, so for instance, when you derive from, after making these approximations, when you derive this Hamilton-Jacobi type equation, it then gives you these, you know, surfaces of level S and then and now what's then done is I whip out a parameter t and parameterize those surfaces.
Okay.
And so I have no objection to that. That's what's normally done in Hamilton-Jacobi theory. That is completely natural. And so there I'm just parameterizing a bunch of things that are already there, that those structures, or approximately there, I guess. But the objection really is about, well, how did I justify that approximate? How did I justify the approximation in the first place? And so there I don't see, so there it's more like, again, I'm putting my hand over a bunch of degrees of freedom and a bunch of correlations and say, don't look over there. But then I want to know why should I not look, or why are they not relevant? They're part of the world, they're part of the physics. And I don't see, and so there I don't see that there I don't see, that it's just a parameter being used, or that there it just seems like I'm being told, don't look, ignore those degrees of freedom, and I'm asking why. And then if you then have to use a kind of time metric or separation of time scales, then that looks bad, I think, for the derivation. So on the one hand, I don't object to the use of a parameter, because that's sort of what I'm doing. That's what I'm doing also with the Schrodinger equation. That's and defining the time. So I'm completely on board with doing that, but I still think there's something pretty questionable in the justification of the use of the approximation.
So the problem, maybe it's the approximation itself, and not the fact that it implies that involve the time t. So
yeah.
Okay. And the related question, more general, given the role of this time t, that is just a parameter, would it be better to say that we don't want to recover time from a bottom level theory with no time? What we struggle with is that we want to recover the change of the word. So we can, so the question will be that if we can explain change without a time t. So the fact that is that I can see the problem where if you have the Wheeler-DeWitt equation without the time t. So it's quite natural that you want to have a time t, or even classically there is a problem of time, because general relativity is a fully parameterized constraint theory. So what do you think about this fact that that maybe we don't want to recover the time t? We don't want to make the time t emergent. We don't want that there is an emergence of changiness of the word, not the time t. We don't need the time t to describe the word. I mean, I can describe even classical mechanics without a parameter time t. I can write the classical mechanic in let's say the configuration of space with how a variable varies with respect to another variable, and I can describe how this span falls in the floor. So maybe the problem is about change and not to recover time.
So are you thinking about something like Ravelli's kind of picture? Is that what you have in mind?
Yeah.
I mean, I think ultimately you need to make sense of the evidence, and if change in observables is enough, then that's fine. You might not get, of course, a time like a time variable, right? So I mean, if we think of general relativity, what we basically have is an indefinite, an infinity of proper times on all the particles of the world. And, then when they all kind of come together and we approximate, them having, so if we look at just like the big galaxies, then we can sort of say, and then we blur our vision, then we can say, there's a cosmic time there. But really, that's just an approximation, and there's really just all the zillions of clocks attached to each particle. And so it's not a kind of a time. And so if we wanted to sort of decompose that minimal type of time into a bunch of observables, or kind of Einsteinian coincidences of particles hitting each other or something, and just have this sort of big kind of like Humean map of all the coincidences or something. Yeah, that would be fine by me. There would not be there would still be time though, I think, in some sense, because I would still be able to then recover all of if we're just thinking classically, I could still recover all the, it would still ultimately be equivalent to general relativity and all those proper times of all those different particles. Well, I guess what I'm trying to say is, so I'm not sure exactly what the move from thinking about change versus time, if that like saves if that really helps all that much.
Okay. Thank you.
Are there other questions? No? Yeah, Alvaro.
So you mentioned something about recovering time from the phase of the wave function, something like that. Can you maybe expand?
You broke up a little bit.
Oh, sorry. You mentioned something about recovering time from the phase of the wave function. And maybe can you expand a bit on that? Because I'm thinking that, if I'm correct, like solutions of the Wheeler-Dewitt equation are real, so they don't have a phase. So how can you make that work? Or
Yeah, so you would have to have so this would be like a kind of, if you were Bohmian, you would need to get the wave function is going to have to be complex, so that you could get some time development. This would be like a kind of argument against the Hawking-Hartle wave function and in favor of a Vilenkin wave function. So one of them would not be useful for you. But and then also it could, so then the other thing too is, of course, that if you're a Bohmian, the wave function of the universe can have many properties that the effective wave function does not have, and vice versa. So the wave function of the universe might be time independent, but the effective wave function could be time dependent. One could be complex, one real, one complex. So, you look at the child, and sometimes the children look like their parents, but they don't have to. And so the big mama wave function need not have the same properties as the effective wave functions.
right, but for describing the movement of particles or whatever Bohmian basic stuff there is, I guess you have to look to the big wave function, to the wave function of the universe. That is where the problem is.
Yeah. But you could definitely have it so the big wave function is time independent, but the smaller wave functions are time dependent. The effective wave functions are time dependent.
Okay, another question I had.
So back in the early 90s, everyone was flipping out about the Wheeler-Dewitt equation, and then I think about 6 different Bohmian groups all looked at this and thought, what's the problem here? We know we can get non-trivial motion. We know we've got another time in the guidance equation. And so Anthony Valentini, he published something. A Ukrainian Bohemian named Shatnov, he published something. Holland and Holland's group published something. Weingart and I published something. And then later, yeah, Shelley Goldstein and others published something on this. But also, yeah, Greensight and others. Even then, other people. A lot of people notice. You ever see that joke, that joke YouTube video that motivates Bohmian mechanics, where it looks through one of the classic like Sakurai quantum mechanics books, and they derive V is proportional to grad S, and then the YouTube video shows that, and it crosses out the proportional, puts equal, and then it says stop the bullshit, and then ends. Anyway, so it's pretty natural anyway in quantum mechanics to then think of the V as proportional to the grad S, and then of course where you've got V, you've got T, and then to think, well, that defines my T throughout the space of solutions.
Right.
Yeah.
Okay, so if there are no other questions, no remarks, we thank our speaker again.
Thank you very much for all the great questions.
And we'll see again for our next meeting on the 26th of October. Thank you very much.